Hey everyone, back in a new awesome video, and today we're going to continue with our series about classical mechanics. Sorry for the long time that passed between my last video and the one before it, but I had already recorded but I couldn't find any time to edit it. I was really busy with my final exams, also applying to universities, and I couldn't get time to edit it. Luckily, I think that from now on, I will try to stick at a 1 week per video schedule, but I don't know if it will be possible. Today, we will explore the fundamental concepts that are useful for analyzing circular motion. We will first introduce polar coordinates, then we will treat velocity and angular velocity in this coordinate system, and finally we will explore different types of acceleration that arises in this situation: angular, normal, and tangential. So let's start! Alright, so let's start with polar coordinates. As usual, we will have our reference frame with the origin. This is going to be the x-axis, this is going to be the y-axis, and we will denote that by our unit vectors I hat and j hat. We will have our mass m right around here, and we will let it go around in circles around the origin. To analyze this situation, the most useful coordinate system isn't Cartesian coordinates as we are used to, but polar coordinates. In this new coordinate system, we will denote the angle between the position vector r and the x-axis as theta. Then we need to define new unit vectors, and we are going to define them in terms of this theta. We will define the r hat vector that is going to be pointing in the radial direction, and we will define the theta hat vector that is always going to be tangential to this circle. To denote a point in this coordinate system, we need to indicate the distance from the origin and also the direction in which this distance has to be measured. We note that, imagine for example, theta in this case is pi over 4, and this is a unit circle. Therefore, our coordinates could be 1 over pi over 4. However, another possible coordinate pair for our point over there could be minus 1, pi plus pi over 4. That is this direction. To avoid this, we will let r go from 0 to infinity, and we will let theta range from 0 to 2 pi. That way, there's only a single way to express every point in the Cartesian plane. Another important feature about this coordinate system is that, imagine our mass at a later time is found right around here and has a brand new theta angle right there. It will also have different unit vectors, r hat and theta hat. And r hat in green, well, that's the position vector, but we mean r hat will not be equal to the blue r hat. And the same will happen with theta hat. They will be completely different coordinates. To understand this, it will be useful to express our new unit vectors in terms of our Cartesian unit vectors. To understand how these vectors are related, we will draw a small diagram for our theta angle right over there. And we'll draw it in big. Let this be the I hat vector and this over here be the j hat vector. If we have a more or less small theta, that will mean that r hat is going to point in this direction, r hat. This is going to be the angle theta, and theta hat will point in this direction, as these two make 90 degrees, and this will also be the angle theta. Now, doing a bit of trigonometry, we find that r hat equals cosine of theta in the I hat direction plus sine of theta in the j hat direction. The cosine of theta is this part up until here, and the sine of theta is this part up until there. Similarly, theta hat will be minus sine theta in the I hat direction, as it is pointing that way, plus cosine theta in the j hat direction. And this relationship will be very useful, and therefore I'll box it. Now let's explore what happens if we let our angle theta right around here have time dependence. So we will make theta equals theta of t. We know that our position vector is going to be equal to the distance from the origin times the r hat vector, and this is the one that is going to be responsible of the circular motion. For now, we will let r be constant, as we are examining only circular motion. Further on, we might let r be non-constant. Now let's see what the velocity will be. V is equal to dr dt, and as we said, r is going to be time independent, and therefore it can go out of the derivative, and we will get that this is equal to the time derivative of the position vector. Specifically, this is d dt of cosine theta of t in the I hat direction plus sine theta of t in the j hat direction. If we carry out this differentiation, this is equal to r times cosine theta goes to minus sine theta, and we get by the chain rule another term d theta dt in the I hat direction, and the sine theta goes to cosine theta of t once again, and we will get the d theta dt term. Then let's take the d theta dt out of the parentheses, and we have d theta dt minus sine theta. Let me drop the time dependence of those. Let's just assume it's in there, and the j hat direction. But this expression is familiar, and indeed it is the theta hat vector. Therefore, we will have that the velocity is equal to r times d theta dt in the theta hat direction. And thus, now that we have an expression for our total velocity, it's time to introduce a new concept, angular velocity, that will help us analyze these situations. But first, we need to introduce a little bit of notation. When we have a Cartesian plane in this direction, and we have our I hat and j hat vectors, we need to define these two symbols. This one is going to mean that there's a vector pointing into the plane. So into the whiteboard in this case, right in that direction. And if we have this type of notation, this will mean that there's a vector out of the plane, pointing out of the plane. So in this direction, in this case. That way, we will define our k-hat vector, the vector pointing in the theta hat direction, in the z-axis. And this will have to always follow the right-hand rule, so that our 3-vector coordinate system is consistent with all the other ones that people make. This works in the following way. You first point your hand towards I hat. Then you curl your fingers towards J hat. And the direction in which your thumb points is going to be your k hat vector. This has to work for every coordinate system that you draw. For instance, this coordinate system won't be valid, as this doesn't work. Alright, now that we have introduced these notions to examine 3D motion, we will introduce angular velocity. When you have a mass that is revolving around the origin in this direction, we will define a quantity. Imagine the mass is right here, and this is the angle theta, time dependent. We will define the quantity W, which its absolute value is going to be d theta dt. Absolute value. However, we would like this to be a vector, so we'll make it a vector, and we will also like it to indicate the direction of rotation. Therefore, we are going to define our angular velocity vector as pointing perpendicularly to the plane of rotation. Furthermore, we're going to define it in such a way that it follows the right-hand rule if it's positive, and it doesn't if it's negative. Let's see what I mean with this. If the direction of movement is in this direction, and we have our angular velocity in this direction, we will have a positive angular velocity, as following the definition of our k-hat vector. Furthermore, if we have the opposite sign of rotation in this way, we curl our fingers around the axis of rotation, and we find that we have a negative angular velocity following the convention of our k-hat vector in this case. Therefore, we can re-express our velocity as v equals r times wc, that is the c component, the k-hat component of the rotation in the theta hat direction. This angular velocity will be very useful, and furthermore, this notion of rotational vectors, or vectors that indicate rotation pointing perpendicular to the plane of rotation and also following this right-hand rule, will be very useful all over our analysis of circular motion. When we introduce angular momentum, torque, acceleration, etc., this will be a convention that we will always follow. Great! Now that we have explored velocity, the next logical step is to explore acceleration. Let's first examine our usual acceleration, that is a equals to dv dt. Then this will be ddt of r times d theta dt times theta hat. So we're going to have three components. Once again, we will assume, however, that r is time independent. So we will let it go out of the derivative and we will have this equal to r times d squared theta dt squared and theta hat plus r d theta dt times d theta hat dt. We see there's two very different components in this case. Let's start analyzing this one. This component is going to be called a tangential, and we will soon see why. If we have our circle in which our mass is revolving, I'll skip drawing the reference frame so that the picture is more clear. We will have our mass around here, our mass m, and once again this will be our unit vectors r hat and theta hat. And we can see that this component of velocity, of acceleration, it's always going to be pointing in the theta hat direction. So right around here, theta hat. Therefore, we can see that this component is always tangential to the trajectory, and that is what makes us call it tangential velocity. Tangential acceleration, once again. We can see that this is another thing expressed in terms of w, that r times dw dt. wc in this case pointing in the theta hat direction. And we will define a new quantity that is going to be called angular acceleration, to be defined as the derivative of our angular velocity. And the direction of this vector will be defined in exactly the same way as our angular velocity vector was. If we have r hat and theta hat, or let me write I hat and j hat, it's the same for both cases. We have our k hat vector, and if we have polar coordinates, we do the same, first with r hat, then with theta hat, and we have the direction for k hat, so that both directions are coherent. Then, if the acceleration is in this direction, that means this component is positive, we will have a positive component of alpha, of angular acceleration, in the k hat direction. If the direction of acceleration is the other one, this will be negative and it will point in a minus k hat direction. So these are two very important accelerations. This is also a vector, and you can see they are closely related in a similar manner than the velocities are. If v equals r times w, we have that a tangential equals r times alpha. So they're pretty analogous. Now let's treat the other component, but let's clear up the board a little bit first. Let's explore this component now. We can see that we have a d theta hat dt term that we haven't explored yet. So let's see. That is d dt of theta hat, which we have over here, and that is minus sine theta I hat plus cosine theta j hat. Once again, we will do all the differentiation and we will get that the minus sine goes to minus cosine of theta times d theta dt in the I hat direction, and this goes to a minus sine theta d theta dt in the j hat direction. We can take out of this expression the d theta and plug it in here. So we will have this component we're going to call a normal, n for normal, or centripetal, as you will see now, and we will see that this centripetal acceleration or normal acceleration is going to be r d theta dt times d theta dt, which we call is angular velocity, the modulus squared, times minus cosine theta I hat minus sine theta j hat. But once again, this component is familiar to us because it's nothing else than minus r hat. Therefore, this is equals to minus r w squared in the r hat direction, and it points in this direction, minus r hat. This formula will be very useful as it relates the force that will make this go around in circles with the radius of the object and also the angular velocity, which allow us to find the period or find the frequency and lots of other things. A very common way to see this expression with another way is to substitute this relationship in a way. We call that B equals R times W. All of those are vectors. Now we will substitute W in here, the angular velocity, and we will get that AN equals minus B squared, and it will be divided by R over 2, but one of those cancel, so we get this, and in the r hat direction, which is a formula you will see most of the times. These are the fundamental concepts that will allow us to make a more deep analysis about circular motion. That is all for today. I hope the video helped you understand the most fundamental concepts that let us analyze lots of different situations in which rotational motion is involved. Any doubts left? You may ask them in the comment section and I'll try to answer them in the best way I can. Remember to like the video if it was the case, and also to subscribe to the channel and press the bell so that you don't miss any of the new videos. I hope you liked it, and see you another day with more Physicawesome!